Einstein was at first dismissive of this. He thought it was just like, oh, the mathematicians are over-formalizing again. But then he later realized the fusion of quantum mechanics and Einstein's theories of relativity has shaped the modern world. Now quantum computers are revolutionizing our understanding of black holes. For decades, these cosmic giants have been among physics' greatest mysteries, regions where gravity is so strong that even light can't escape. But with groundbreaking advances in quantum computing, scientists are now probing the very fabric of black holes like never before, and their findings are rewriting the laws of physics. Black holes were long considered one-way streets. Anything crossing the event horizon, matter, light, even time, was thought to be lost forever. But quantum mechanics suggests otherwise. Information, the fundamental building block of reality, can't just vanish. This paradox has puzzled physicists for over 50 years, and now quantum computers may have uncovered the answer. The journey starts with a mind-bending idea called holography, the concept that black holes aren't what they seem. Instead of being three-dimensional objects, they might actually be two-dimensional surfaces that store information like cosmic hard drives. This radical idea, known as the holographic principle, suggests everything inside a black hole is encoded on its surface. But proving this required calculations far beyond classical computers, until now. Using quantum computers, scientists have simulated microscopic black holes and tracked their information dynamics in ways never possible before. These simulations revealed something astonishing. Rather than simply swallowing information, black holes seem to scramble it and eventually release it, resolving the information paradox. And that's just the beginning. For years, physicists have been caught between two competing theories: general relativity, which explains gravity on cosmic scales, and quantum mechanics, which governs the subatomic world. Black holes sit at the intersection of these frameworks. They form from the gravitational collapse of massive stars, but their interiors defy classical physics, existing in realms dominated by quantum effects. The problem: general relativity predicts black holes should contain singularities, points of infinite density where physics breaks down. But quantum mechanics insists information can't be destroyed. If information falls into a singularity and is lost, it violates one of quantum theory's core principles, unitarity. This is the infamous black hole information paradox. For decades, physicists have struggled to reconcile these contradictions. Theoretical models like Hawking radiation suggest black holes slowly evaporate over time, leaking energy into space. But where does the information go? Is it really lost, or does it somehow escape? Classical computers were too limited to explore these questions. The calculations needed to model black hole evaporation are overwhelmingly complex, involving billions of interacting quantum states. Enter quantum computers. Unlike classical computers, which process data in binary code, ones and zeros, quantum computers use qubits, quantum bits, that can exist in superpositions of multiple states at the same time. This enables quantum computers to tackle problems that would take classical machines longer than the universe's age to solve. Recent breakthroughs in quantum computing have allowed researchers to simulate small-scale black hole analogs. These simulations suggest something extraordinary. Information falling into a black hole isn't lost forever. Instead, it becomes scrambled and encoded in Hawking radiation, hinting at a possible resolution to the information paradox. Scientists at institutions like Caltech and MIT have used quantum circuits to model how information flows in black holes. By entangling qubits and simulating quantum gravity, they've demonstrated how information might escape from an evaporating black hole. These findings support the idea that black holes function like quantum computers themselves, processing and storing information in ways previously unimaginable. But the implications extend beyond black holes. If black holes don't destroy information, our entire understanding of space-time needs re-evaluation. The fabric of reality itself may be deeply quantum in nature, with space and time emerging from fundamental information and processing. One of the most exciting uses of quantum computing in black hole research involves wormholes, hypothetical tunnels in space-time connecting distant parts of the universe. Recent quantum simulations suggest entangled black holes could behave like wormholes, allowing information to pass between them instantaneously. This could offer the first concrete evidence of quantum teleportation on a cosmic scale. Physicists have long speculated that black holes and wormholes might be two sides of the same coin. The famous ER equals EPR conjecture, proposed by Juan Meldacena and Leonard Susskind, suggests wormholes, Einstein-Rosen bridges, and quantum entanglement, Einstein-Podolsky-Rosen pairs, are fundamentally connected. If true, it means quantum computers aren't just tools for simulating black holes, they're windows into the deepest structure of reality. Recent quantum experiments have provided the first hints this might be the case. By creating quantum circuits that mimic the entanglement patterns in black holes, researchers have observed behaviors consistent with wormhole-like information transfer. While these are early results, they suggest black holes might not be just one-way traps but gateways to deeper quantum realities. This raises a profound question. If information isn't destroyed in black holes but transformed and released, could it be possible to reconstruct what falls into them? Some physicists believe future quantum computers will be powerful enough to decode the information stored in Hawking radiation, effectively allowing us to see inside black holes. If true, this could unlock secrets about the universe's origins, the nature of time, and even the possibility of multiverses. Black holes are no longer just cosmic mysteries. Thanks to quantum computing, they're becoming laboratories for the ultimate laws of physics. As we continue to advance computation in quantum theory, we may soon discover that black holes hold the key to understanding the very nature of reality itself. This marks the dawn of a new era in black hole physics. For over a century, black holes have remained some of the most perplexing objects in the universe. Einstein's general theory of relativity first predicted their existence. It wasn't until the late 20th century that black holes became a serious focus of study. The discovery of Hawking radiation in the 1970s opened new questions about their fundamental nature. Now, in the 21st century, quantum computing has brought us to the edge of answers once thought impossible. Quantum simulations of black holes are revolutionizing how scientists study them by allowing unprecedented modeling of their behavior. Unlike traditional supercomputers, which struggle with the complexity of quantum gravity, quantum computers process information differently by leveraging superposition and entanglement. Recent experiments at institutions like MIT, Stanford, and Google's Quantum AI Lab have used quantum processors to simulate black hole dynamics. By creating quantum circuits that mirror the mathematical structure of event horizons, researchers have tested theories that were once purely speculative. One of the most remarkable breakthroughs occurred in a 2022 experiment where physicists used a quantum processor to simulate a microscopic wormhole. While not a literal wormhole in spacetime, the quantum system behaved exactly as theoretical models predicted a wormhole should. This simulation provided compelling evidence for the ER equals EPR conjecture, suggesting that wormholes and quantum entanglement are two aspects of the same phenomenon. What this means for the information paradox. The black hole information paradox has been one of the most persistent mysteries in physics. If information were truly lost in a black hole, it would violate quantum mechanics' principle of unitary evolution. However, quantum simulations now suggest that black holes do not destroy information. Instead, they seem to scramble it in complex ways and release it slowly via Hawking radiation. A breakthrough paper from Caltech in 2023 showed that quantum computers could reconstruct information from simulated black hole radiation. By combining machine learning with quantum algorithms, researchers decoded patterns in the radiation that hinted at the original quantum states that had fallen into the simulated black hole. This implies that, in the future, sufficiently powerful quantum computers could theoretically retrieve information from real black holes, potentially revealing what has fallen into them over cosmic time. Black holes as quantum computers. The implications extend beyond black holes. If black holes process rather than destroy information, they might function like quantum computers. Some researchers even believe black holes could be the universe's most efficient information processors. Leonard Susskind, a pioneer in black hole physics, has proposed that black holes may act as fast scramblers of quantum information. This means instead of erasing data, they transform it into complex quantum states that are practically, but not fundamentally, impossible to decode without advanced quantum computers. If black holes are indeed quantum computers, they could unlock the key to understanding the fundamental nature of reality. The idea that space and time emerge from quantum entanglement is gaining momentum in the physics community. Quantum simulations suggest that space itself may be woven from a vast network of quantum entanglements, much like the structure of a quantum computer. Could black holes be portals to other universes? One of the more speculative yet intriguing ideas emerging from quantum computing research is the possibility that black holes could serve as bridges to other regions of spacetime or even entirely different universes. The idea of black holes as gateways isn't new. Physicists have long explored whether some black holes could be connected to white holes, hypothetical objects where matter and energy emerge instead of being pulled in. If this is true, black holes might act as cosmic tunnels through spacetime. Quantum computing has added a new layer to this theory. By simulating quantum teleportation protocols on quantum processors, scientists have observed behaviors resembling wormhole-like connections. If black holes and quantum teleportation are linked, entangled black holes could serve as cosmic shortcuts, enabling information and potentially even matter to traverse vast cosmic distances instantly. The future of black hole research with quantum computing. With quantum computing technology still in its infancy, we're only beginning to uncover what's possible. Yet, the progress over the past few years hints that within decades we may have the computational power to simulate entire black holes with incredible precision. Future quantum simulations could help answer some of the most profound questions in physics. What happens at the singularity inside a black hole? Can Hawking radiation be used to recover complete information about objects that fall into black holes? Are black holes truly quantum computers? And if so, what does that imply for the nature of spacetime? Could black holes be engineered or manipulated using advanced quantum technologies? These questions, once purely theoretical, are now within reach of real experimental exploration. Black holes, consciousness, and the simulation hypothesis. Perhaps one of the most unexpected implications of these discoveries is their impact on philosophical questions about the nature of reality. If the universe behaves like a quantum computer, processing information similarly to black holes, some scientists propose that reality itself may be fundamentally computational. The idea that the universe is a giant quantum simulation has gained traction among physicists and philosophers. If black holes can store and process information at a fundamental level, they might act as cosmic memory banks, recording the universe's history in ways we don't yet understand. This leads to another profound question. If black holes process information, could they possess some form of consciousness? While purely speculative, this idea has inspired researchers to consider that consciousness itself might be linked to how the universe processes information. If black holes encode and transform information rather than destroy it, understanding their inner workings could offer clues about the fundamental nature of thought, perception, and reality itself. The next steps toward a unified theory of everything. Studying black holes through quantum computing is guiding us toward something even more significant, a unified theory that combines quantum mechanics and general relativity into a single framework. This has been physics' holy grail for over a century. The discoveries emerging from quantum simulations are offering new insights into the deep structure of reality, suggesting that gravity itself may emerge from quantum information processing. If this is true, then black holes are not just mysterious cosmic objects, but rather key pieces in the puzzle of the fundamental nature of the universe. In the coming decades, quantum computers will continue to advance, allowing scientists to simulate ever more complex quantum gravitational systems. This could lead to breakthroughs in fundamental physics, space exploration, and even new forms of technology based on black hole-inspired computation. We are standing on the edge of a new scientific revolution, one in which quantum computing and black hole physics converge to unlock the greatest mysteries of existence. The question is no longer whether we can understand black holes, but rather how deep into their secrets we are willing to venture.